Not that amazing. I mean, at first people thought, well, interest rates couldn't possibly be negative, but really, it may well be that you're earning a negative return on your checking account because, a negative return just means that you're paying for the service of having a deposit at the bank. So they probably don't state it for you as a negative interest rate, but if you put your money in the bank, you're probably earning, in your checking account, probably earning zero interest, but they're also charging you fees. So the Central Bank of Japan, when they're setting a negative interest rate, I mean, effectively now what they're doing is banks that have deposits at the Bank of Japan are paying a fee for those deposits. And at first, as I say, up until a few years ago, people were a little bit dubious about the idea of negative interest rates because you could always hold your money as cash, and cash earns zero interest. So, why would you accept a negative interest rate? But think if you're a bank, why would you accept negative interest rates? Well, because it's inconvenient to hold, billions of dollars of cash. And so if you're, especially also if you're a bank and you need to make transactions with other banks, which you make through the central bank, then it's you're willing to pay to have your money on deposit at the central bank. So in many ways, this idea of a negative interest rate, which really hadn't come up until a few years ago, is surprising, but then when you think about it, it's not that surprising. It's just a fee. But actually, the question I want to ask is, in the models we've been looking at, can the central bank set the interest rate like the Bank of Japan just did, or the Fed, in December raised the short-term interest rate? In our model, can the central bank do that? Yeah.
No, because it's smaller.
Well, that's part of it. It's a small open economy, but that's only part of it. It is correct that they cannot, but there's more to it than that. Yeah.
Are we taking like a world interest rate?
Well, that's that was his comment, that we're taking the world interest rate. But suppose we took the closed economy version of this model. Suppose there was no rest of the world. So then, this was like those we took 312 from me. That was like the model we did there. I mean, can a central bank set the interest rate in the closed economy version of this model? I mean, and really what I'm asking you is whether you kind of understand basic macro at a kind of a first-year level. And it's hard because you hear it and you take notes and you take a test and you forget it, but it's kind of important that you understand this. Yeah.
There's no money supply.
There's no money supply. That's right. So what if we? That's a big part of this. What if we introduced a money supply, or what if we introduced a central bank and money supply? Then could the central bank set, this R1, for example? Okay, let me ask this question. So you've probably done like an ISLM model or something like that. Who's done macro where you have, okay, there's an interest rate in that, and monetary policy influences that interest rate. Is this the same thing? Is this the same kind of model? Does monetary policy influence the interest rate the same way here? All right, and don't waste my time. Just answer the question. If you know the answer, I'm a busy guy. Don't sit there and be afraid to say something. All right. Well, then I'm just not going to lecture, because, really, seriously, somebody answer. I don't like this business of sitting there and not saying anything. Yeah.
I don't think central bank fixes the interest rate. Because like in the model we have seen, like you have basically you have the interest rate, So like the central bank is modeled between the change in the interest rates, which is the short-term interest rates in the central bank, and the interest rates of this household, we should take into account that there is a sort of transmission mechanism. Maybe the effect on the interest rate of the household would not be this. So
Well, you're getting at it, and let me put it this way. What's the fundamental difference between an ISLM type model and this model?
Prices?
Who said prices? Prices. What about prices?
That in the ISLM is greedy prices,
Yeah.
static prices, and in this model is like
Right. So they're rigid nominal prices in an ISLM model, and this model has flexible prices. Okay, what's the difference? There's another difference now I want to focus on. Typically, when we write down a money, like if you in ISLM, you write down a money demand equation, and there's an interest rate in that money demand equation. How is that different from the interest rate we're looking at here?
because this is a real interest rate.
Sorry,
Because our interest rate is a
real interest rate, and it's a nominal interest rate in the money demand curve. So remember that there's such a thing as the nominal interest rate, call it IP, and it's equal to the real interest rate plus, I'm going to use this notation because we'll use it later in the lecture today. That's the expected rate of inflation. Pi is the inflation rate between t and t plus 1. And really, I just feel like 2/3 of you knew this and weren't raising your hands. And let's just not do that because I don't know if you're afraid to say something, but just say it. Don't waste my time, like I said. So anyway, this is the nominal interest rate. This is the real interest rate. This is the expected rate of inflation. Or a different way of saying it is that the real interest rate is the nominal interest rate minus the expected rate of inflation. Now, what we have in this model is a real interest rate, right? A real interest rate is you put aside a unit of a good today. This is how much goods you receive a period from now. Or as I was saying in my 302, my intermediate macro class, like you have $100, you could go to Target today and buy a handbasket full of goods, or you could take that $100, put it aside in a saving account, and the real interest rate tells you how many goods you can put in that basket a year from now. It's the increase in the number of goods that you can get. The real interest rate then would be the nominal interest rate minus the expected rate of inflation. So, if the bank is offering a 5% nominal interest rate, that doesn't necessarily indicate the increase in your purchasing power because there could be inflation. So you're earning 5% at the bank, but if there's 2% inflation, then your real return is only 3%. That 5%, 2% of it is eaten away by inflation. So, the real return gives you the increase in the number of goods you get from saving. Or if you're a borrower, it's how much you have to pay in real terms. Now, in the model we're looking at, we only talk about the real return. So we talk about people saving, putting aside a unit of the good today and earning a return of R star tomorrow. Now what if we, let me ask this question. Let me make the statement that, the Fed, when you say the Fed is, controlling the interest rate or doing something to the interest rate, like the Fed funds rate, or the European Central Bank is changing the interest rate, or the Bank of Japan, that's the nominal interest rate. When they talk about that in newspapers, they're talking about the nominal interest rate. Can the central bank affect the real interest rate? Now I'm talking about the real world. I'm not talking about our model. Yeah.
Yeah, I was thinking expected, or the
mean, yeah, they can, but does that affect the real interest rate? So there are two components, and you're saying they can affect this one. But what about this one? Can they affect that one? Yeah.
I mean, indirectly they can, because if they set the nominal rate and the expected rate of inflation, there's not much else left. But they can't directly say the real interest rate is going to be a certain amount.
No, that's right. But let's talk about models. In the ISLM type model, can they affect the real interest rate? Yeah.
In the long term, the central bank cannot affect the real interest rate because it's going to cause inflation. I mean, if you reduce, for instance, the interest rate, it's going to stimulate the demand agree, and it's going to cause inflation. So in the long term, it should not have any effect, any real effect in the long term.
Yeah.
Monetary policy.
But what about when you're not in the long term?
Yeah, I mean, that in that case it should affect.
Right. So when we look at an ISLM model and we say the central bank is changing the nominal interest rate, has an effect on the real interest rate. Why? Well, because as you said before, nominal prices are sticky. How does it change in the real interest rate affect the economy in an ISLM model? Hey, stop looking at looking down. I mean, hey, if you really don't know this, then you should just go back and study your 302, or that's intermediate macro, because you really ought to know this kind of stuff. And as I say, I don't actually believe you don't know it. You're just embarrassed. You're not used to a class where you're used to being not speaking up in class. As I say, my time is valuable. I don't like these pauses where people don't talk. So I say, well, I already forgot what I was asking now, but this is like my overall grade distribution for the class is falling because I don't like I really just don't understand this failure to participate. Let's ask it again. How does a change in the real interest rate affect the economy in an ISLM type model, in a Keynesian model, when the monetary policymaker changes the interest rate? What are the channels that the real interest rate works through in that? Investment is the main one, so that's the thing we focus on. Like if they tighten monetary policy, it raises the real interest rate. If they lower, if they ease monetary policy, it lowers the real interest rate. And that an increase in the real interest rate would reduce investment demand. A drop in the real interest rate would raise investment demand, and that in turn has effects on the economy. If demand for investment goods goes up, that will stimulate the economy. There'll be more output, but then also in the long run more inflation. And none of that's going on in the model we're looking at. Okay, and you can imagine adding a monetary sector to our economy, but in our economy, monetary policy wouldn't affect the real interest rate. Okay, why not? We already covered this. Why wouldn't it affect the real interest rate in our economy? Somebody already said this. We talked about it already. Because it's so sad.
There's no money.
Well, say there was money though. Let's put money into the model. You could imagine adding money to this model. For example, you could say the price level is equal to the money supply. There's a simple model of the price level. So why does the change in the money supply affect the real interest rate in the Keynesian model, but not in this model? Yeah, prices are right. They're flexible. They change freely in this model. So if there were nominal prices in this model, they would be just freely changing. And so maybe the central bank could affect inflation, but they couldn't affect the real interest rate. So we're looking at a fundamentally different kind of model than the ISLM model here. The model we're looking at, the real interest rate by, saving and investment decisions in the world economy. Actually, this small open economy takes the interest rate as given from the rest of the world, but it's a real interest rate. It's not an interest rate that's controlled by the central bank, and even if the central bank could control the nominal interest rate, it couldn't affect the real interest rate here because prices are flexible. And by the way, let me just say one more time. You think you're afraid to say something because you're going to be embarrassed that you'll say something wrong. And you don't want to embarrass yourself in front of your classmates and me. I think you're embarrassing yourselves by not saying anything. And so that's the last I'll say about it. But all right, so let's go on to the model. So let me just review where we were last time. We're looking now we're trying to build up an understanding of the current account. And we've started with a small open economy. Initially, we just looked at households who saved and output was just given. Then, in that case, the current account was just equal to saving because in general the current account is saving minus investment, but there was no investment because output was not produced. It was just equal to output. So now we're still working with a really simple model. It's a model of a small open economy, but there's output is produced, and it's produced using capital. Capital comes from investment. So now there's an investment decision, and if you remember, we said, well, in this simple two-period model, the only chance you have to accumulate capital is between period 1 and period 2, and the firm accumulates capital so as to maximize its profits. And so we had the profit function up there for the firm in period 2. The profit function was the difference between its output and its cost. This is its output, but it's also its revenue because there's only a single good in this economy, and so revenue is equal to output. The price of the good is normalized at 1 because there's only one good. And then its only cost is the cost of the investment. So this firm had to borrow to finance its investment, and it has to pay back interest in period 2. So its profits in period 2 are the difference between its revenue and its cost. And so it chooses investment in period 1 to maximize profits. So we just substitute I1 for its borrowing there. And they maximize profits, and we found that the first order condition was that the marginal product of capital was equal to 1 plus the interest rate. And from that, we determined that investment depended on the interest rate negatively and on productivity in the second period in a positive way. And we analyzed this function by taking the approximation and found that indeed an increase in the interest rate will lower investment and an increase in productivity will raise investment. And then we said, okay, now we've got to still have households in the model. What are households doing? Well, households are consuming and saving. So in period 1, this is their consumption C1. Their saving is their accumulation of claims. What's their income? Well, in this model, their income is coming from interest plus profits. Okay, we can take the usual intertemporal budget constraint, and this says that the present value of their consumption is equal to the interest on their initial claims plus the present discounted value of their profits, and we arrive at the same first order condition that we had in the model where output was not produced, where output was just an endowment. That is, for households, you still set the marginal rate of substitution equal to 1 plus the interest rate. Now I want to talk about equilibrium in this economy. So that was all what we did last time. So what's the equilibrium in this economy? Well, first of all, because this economy is taking the interest rate as given from the rest of the world, then the equilibrium interest rate has to be R star. Now, how can that be? How can it be that this equilibrium price is just some exogenous constant? Well, that's because this country can borrow and lend freely with the rest of the world at that interest rate. Okay, so they don't have to determine the interest rate within the economy. There's just some price that's posted, and the economy as a whole can borrow and lend from the rest of the world. Now, here's a key equation in this model, and it makes it different from the previous model. The household's claims, that is the household's wealth, the household's bond holdings, can actually come from two places. One is lending to the rest of the world, or the other is lending to firms. Okay, so in this case, if the household saves, it's not necessarily saving by lending to the rest of the world. It could be saving by lending to firms. And both of them pay the same interest, so that actually the household wouldn't care which one. All right? A different way of saying it is this, that our external claims are equal to our net household saving, or our net household wealth, minus the debt of the firms. Minus the debt of the firms. All right. Likewise, in period 1, this would be true. Now, actually, firms don't borrow in period 0 in this model. Okay, so in this model, the only time firms borrow is between period I guess I have allowed it up here. So let's look at what I've done. So what I have done is take what I'm doing is I'm going to start with the household budget constraint. Then what are the profits in period 1? Well, the firms are endowed with output in period 1. So there's no production of output in period 1. You don't use capital to produce it. There's just an endowment of output. And so the profits are the revenue that it makes, which is Q1. The price still is 1, so it's 1 times Q1, minus the interest that it has on any debt that it carried over from period 0. So it's possible this firm, started with some debt in period 0, and neither of these, Q1 or D0, are choice variables in our model. They're not something the firm is choosing. It can't choose anything that has a time 0 date, because the time in our model just starts at time 1. So anything with a time 0 just came before the beginning of time for the firms. That's how they started. And then Q1, they're not choosing, because that's just an exogenous endowment of output. So that's their profits in period 1. Here's their profits in period 2, and that's the thing we looked at previously, where they're choosing investment to maximize profits. So if we take the household budget constraint, substitute in these expressions for profits, and then substitute in these expressions for foreign bonds, we end up with this expression here at the bottom. So what's the expression at the bottom say? Well, on the right-hand side, we have the present value of this country's spending. So we take the total spending by the country, and the first period spending is consumption plus investment, and then we've got the discounted value of second period spending. There's no investment in period 2 because, there's no point in accumulating capital in period 2 because there's no period 3 where you could use the capital. So the only spending that occurs in period 2 is consumption. On the right-hand side is the present value of this country's stream of income. So it includes the value of its initial claims on the rest of the world, earned with interest because these were the claims that existed at time 0, and then plus the present discounted value of output. So Q1 is output in period 1, and A2 times F of I1 is output in period 2. Notice how for the country's budget constraint, we just have international debt. We just have our international claims on the rest of the world. We don't have these initial household holdings of bonds, and we don't have the initial firm's debt level. Because all that matters for the country as a whole is the net claims, the net assets. So, one way of saying this is suppose initially, in time 0, households had $1 million of wealth, but maybe 600,000 of that was in the form of loans to firms. Then the other 400,000 is the net external debt. So the 600,000 loans to firms are money that this economy owes itself. It washes out. This $1 million of wealth that the households have, well, that's offset by $600,000 of debt by the firm. So the country as a whole, its net wealth would be the $400,000 that of claims that it holds on the rest of the world. So the internal debt cancels out. If I lend you $20, the net debt of this classroom is still 0 because I've got a $20 claim, but you've got $20 debt. The only way we can have claims on the rest of the world is if we make loans to people outside of this classroom. So that's the country's budget constraint, or the country's resource constraint. Any other questions? The last line being the country's intertemporal budget constraint. All right, so now we can characterize the equilibrium of this economy with 3 equations. We still have the same first order condition that we had before in the endowment model, and we have the resource constraint or the budget constraint, which is like the one that we had in the endowment model, only now we've got an additional source of spending on the left side, and on the right side, period 2 output is no longer an endowment, it's produced using an investment. So in the endowment model, we just had the condition that the marginal rate of substitution between current and future consumption is equal to 1 plus the interest rate plus a budget constraint. We still have those 2 conditions, it's just that the budget constraint's a little more complicated. But we have a third condition, which is the profit maximizing condition of the firms. So to have an equilibrium, the households have to be maximizing, so they have to be at the point where their indifference curve is tangent to the budget constraint. The firms have to be maximizing, so they're hiring capital up until the point where the marginal product of capital is equal to the gross interest rate, and then the country's budget constraint has to be satisfied. So those 3 equations together are going to determine the 3 endogenous variables, which are C1, C2, and I1. those are the only endogenous variables. Those are the only variables determined in this model, C1, C2, and I1. R star is exogenous because it's given from the rest of the world. R0 and B0 star are exogenous because they were determined before the economy started. A2, productivity in period 2, is exogenous. And that's it. So only C1, C2, and I1 are endogenous. And so again, we're kind of in a situation where we want to look at these equations and analyze them, but we can't solve them explicitly. Now, on your homework, you're lucky enough, you can solve them explicitly. So if you started on problem 2, which is one I assigned out of the book, that's one where you can solve it explicitly because they give you a utility function and they give you a production function and you can solve it. You know, good luck to you, boy. I thought it was going to be one with nice, sensible numbers, but no, it's not. So have fun with it. Anyway, so how are we going to analyze it? Well, you know, in the endowment model, we could just analyze the equilibrium graphically. There were only 2 equations, and so we could look at a 2-dimensional graph and look at the solution for C1 and C2. Those were the only variables we were trying to solve. Here it's not so easy because there are actually 3 variables. We could use a 3-dimensional graph. Now, in fact, you can see that investment in period 1, I1, is actually just determined by the last equation. So, you know, you could still look at the first 2 equations graphically, right? So you could say, okay, well, given I1, let's you know, draw a budget constraint. Draw a budget constraint. Let's draw the map of indifference curves, and I'll just draw the one that matters. So there's the point where the marginal rate of substitution is equal to the 1 plus the interest rate. And you can work out where the intercepts were, but I think maybe I will, you know, assign that either as a homework or put it on the test to ask you to think about, you know, what are the intercepts now in this graph, and how can you tell if this country was running a current account surplus or deficit using this graph. But I'm not going to do that. Instead, I'm going to say let's analyze this mathematically. So I'm going to introduce some simplifications like we did last time in the last chapter. First of all, I'm going to assume that this initial claims on the rest of the world is 0. So we're just going to simplify the model by assuming this term is 0. And so that simplifies the budget constraint to this. And I've multiplied through both sides of the equation by 1 plus R star, but it's the same budget constraint. And now also, like in the previous set of slides, I'm going to assume that the utility function takes this form. So it's big U of C1 and C2 is little u of C1 plus beta times little u of C2, so that you know there's this little u function that tells you your utility consumption each period, but from the perspective of period 1, period 2 utility is discounted by beta, so beta is a number between 0 and 1. And then we get the first order condition for this utility function just like we had before, given by this equation here. So I've simplified, but I still haven't specified exactly a functional form for little u. And so now I'm going to go through and I'm going to do like I did before. I'm going to take a linear approximation. So that's a linear approximation of the previous equation. So that equation, I'm going to just take a linear approximation. The variable C1, which is endogenous, R star, which is exogenous, and C2. And I'm going to take that linear approximation. But then, again, I'm going to make things simpler by assuming that beta times 1 plus R star is equal to 1. Okay, so I'm going to make that assumption I made before, that the market discount factor is equal to the utility discount factor. There's no reason that has to be true. I mean, both of those are just, well, beta is a parameter in the utility function, and 1 over 1 plus R star is, just the exogenously given interest rate from the rest of the world. But I'm just making that assumption that beta times 1 plus R star equals 1 because makes things simpler. I mean, there's just less clutter up on the board. Okay. And so that reduces this linearization to this. So this is exactly what we did in the previous chapter. Okay. Now we have to take an approximation to the budget constraint. And here, I would urge you to, go back at home and work through these equations, write them down, and make sure you can do them. Start with the budget constraint and do the linear approximation yourself and see if you get the same answer I did. And if you didn't, maybe I made a mistake, or maybe you made a mistake. And so then, if I made a mistake, you can tell me, or if you made a mistake, maybe you'll figure it out, or maybe you think I made a mistake and I'm talking about it. But you should work through that. Okay, but now I'm going to, so this is just straightforward taking a linear approximation to the budget constraint. So budget constraint written this way, where I've gotten rid of the initial data by assuming 0. But notice that this expression actually is going to simplify a little bit because I've got an A2 F prime times DI, and I've got a minus 1 plus R star times DI. But at the optimum, A2 times F prime is equal to 1 plus R star. So that term, that DI, and that DI cancel out. And actually, there's no DI left in the equation. So remember, the variables here are the things with the D's in front of them. And, I'm using this very shorthand notation. Things that are variables in this equation are the things with the D's in front of them. DC1, DC2, DR star, DQ1, DA2. These other things are no longer variables. This is actually I1 at the point of approximation. So if I were being more careful, I would, or into more elaborate notation, I would carefully denote that this is I1 at the point of approximation, and C1 at the point of approximation. I might call it I1 bar, or I1 dot, or I1 hat, or I1 0, or something like that. But I'm not doing that. But all these things that multiply, like dr, or dq, dc, they're no longer variables. They were variables in our original budget constraint. But now these are the values of those variables at the point of approximation. So now they're just constants. Okay? So the variables are dc1, dc2, dr star, dq1, da2. The other things are just constants. Even this f is a constant. That's f of I, but I evaluated at the point of approximation. The only things that are variables are the things with D's in front of them. And we're trying now to solve for DC1, DC2, DI1 in terms of the exogenous variables, which are DR star, DA2, DQ1, and anything else? I guess that's it. So actually, when we do our approximation, look, it's kind of interesting because in in the approximation, DC1 and DC2 are not going to depend on DI. That is, the consumption levels aren't going to depend on the investment levels. The change in investment doesn't appear in this equation, and it doesn't appear in this equation. So in the endowment model, we had this equation, and we had the budget constraint, and there was obviously no investment, and we could use those two equations to solve for DC1 and DC2. Well, interestingly, the same is true in this model. When we do the approximation, investment doesn't show up at all. Investment is just determined by the third equation. Remember, the third equation in our system is this one. And when we do the approximation, investment here is just this equation, which is one we solved for already when we were just looking at the firm's problem. So we already did that approximation, and that approximation solved for investment in terms of the two exogenous variables, R star and A2. We can use those first two equations to solve out for C1 and C2, and here's our solution for DC1 in equilibrium. And so it's got the solution for C1 in terms of Q1, A2, and R star. And it's actually really similar to the solution in the endowment economy. When we solve for consumption in the endowment economy, we saw that what affected consumption in equilibrium was the endowment in period 1, the endowment in period 2, and the interest rate. Okay, so the endowments matter because that was your income, and then the interest rate matter because it determines your saving level. Well, the same is kind of true here. The endowment in period 1 matters, and notice that the coefficient is less than 1. It's 1 plus R star over 2 plus R star. Okay, that's the permanent income effect coming in. If your first period income goes up and your second period income doesn't change, then you don't consume all of it. So the coefficient is 1 plus R star over 2 plus R star. That's less than 1. You're going to save, if you have an increase in the first period endowment, you're going to save some of it and consume some of it. So your increase in consumption is less than 1 for 1 with your increase in Q1. Now, an increase in productivity in period 2 actually just acts like an increase in endowment of output in period 2 in the endowment model. You know, you're just getting more productivity, and so that's going to raise your current consumption. If you expect productivity to be higher next period, then you're going to have higher consumption this period. Now, one question you might have here is that, well, gee, you know, isn't there another effect from the increase in productivity? Because when productivity went up in period 2, you saw that investment went up. And if investment's higher, you're going to produce more output from investment as well. So shouldn't there be an indirect effect as well? I mean, you know, there's this direct effect that higher productivity raises output. So the effect on output is exactly, you know, the initial F times the change in A2. But what about this indirect effect that increasing productivity raises investment, and then if you raise investment, you raise output? Why isn't that showing up as having an effect on first period consumption? Anyone guess? let's think about it. Is the answer that the additional output that comes from higher investment that we just don't need, we don't consume it? Is that it? Yeah.
In this model, we said that the spending equilibrium, your R just R star, which is fixed. Since the investment depends on just depends on this fixed number, then investment is just fixed.
Well, no, investment's actually not fixed. I mean, that's what this equation is saying. So here, I'm saying that let's increase productivity in period 2. That's the experiment I'm doing. And you can see that it affects investment. So I'm going to start at some initial point. You know, say some point where that these 3 equations hold. Okay, and I'm going to take a linear approximation of these 3 equations around some initial point. And now I'm asking, well, okay, now I've got a solution for C1, C2, and I1 in terms of deviations from that initial point. And they're affected by deviations of R star from its initial value, A2 from its initial value, and Q1 from its initial value. And so I said, okay, well, you know, if A2 is higher than its initial value, there's going to be a direct effect because we're going to get more output for any given amount of capital that we use. But also, we know that if A2 is above its initial point, we're going to end up investing more. Okay, this is a positive coefficient here because there's a minus. Now, F prime is positive and A2 is positive, but F double prime is negative because we've assumed concave production functions. So this whole thing is positive. So we know higher productivity if A2 was greater than its initial value. Remember, the idea is dA2 is our shorthand for the difference between A2 and our initial A2. We call it A2 bar. So we have this increase in A2. It's going to lead investment to go up above what it was initially. That definitely gives us more output. We have higher investment. So why aren't we consuming? Why doesn't that affect our first period consumption? Why don't we consume that additional output that's coming from investment? Where is it going? We just giving it away? Are we saying, well, that's nice, we've got this additional output, but we're just going to look at it and not consume it? We're going to hold on to it for the 3rd period when we're dead? So what happens? Why isn't that raising our consumption? Yeah.
But the PC1, you have also the equation of the
Yeah.
So I mean, you should have a rate.
Well, that's the direct effect. What I'm saying is, you can think of their output in the 2nd period of I1. And what we do see up there is the direct effect. So at the initial I1, if A2 goes up, you get more output. But then I'm saying there ought to be, you would think there would be an indirect effect. But if you get more investment, that F of I is going up and you get more output. So now I'm saying, why doesn't that show up? Anybody want to?
Because the investment was already chosen.
Sorry?
Because the investment was already decided what period before.
No, because, you know, in a sense what I'm doing, I guess you could say, is comparing an economy that had productivity A2 bar to an economy with a slightly higher A2. And so the economy with a slightly higher A2 is going to directly have more consumption because A2 is higher, but it also will have more investment. And that ought to be increasing output. So I'll give you a hint. It is true that output is higher. So A2 doubt about that. Output's definitely higher through that indirect effect. Question is, why isn't that influencing consumption? Yeah.
Is it because you're borrowing to achieve that higher level of output?
That's right. That's exactly it. That, we're looking at small changes from the initial equilibrium, and if you increase I1, the effect on output is A2 times prime times the effect times the change in the investment. So if you have a small change in investment, this is the effect of output in period 2. But there's a cost. The cost is the interest cost. So the cost is minus 1 plus R star times DI. So you get the additional output, but at the margin, that additional output is just offsetting the cost of the investment, because at the optimum, you've set the marginal product to capital equal to 1 plus the interest rate. So yeah, you get some additional output, but it gets canceled out because you're paying the higher interest. Actually, that's what happened when we were doing this step here. Back here, we took this approximation to the budget constraint, and then I said, well, this term cancels out with this term. So because that's true, then this term here cancels out with the 1 plus R star times minus DI1. So here's the increase in your income, that indirect increase in your income that I kept talking about, but that's being offset by the increase in your cost of borrowing. So in the end, at the margin, you're not going to get anything. That's actually an application of the envelope theorem, which you may have heard of. But don't ask me to state the envelope theorem, because I'll mess it up. But anyway, so it doesn't show up there. Now, what about the effect of the interest rate on first period consumption? Well, again, just like in the endowment model, there's substitution effects, and then there's these wealth effects. So the substitution effect, the higher interest rate, definitely lowers your consumption. If the interest rate is higher, if you're a saver, you're saying, well, let me save more because I can earn more interest on my saving. Or if you're a borrower, you're saying, well, I want to borrow less because I have to pay a higher interest rate on my borrowing. Either way, a higher interest rate makes you consume less, and so that's the effect. It's beta U prime. That's of course positive, but the denominator is negative U double prime over 2 plus R star. There's the indirect effect, the wealth effect, which is coming if the country as a whole has claims on the rest of the world in the first period. If Q1 minus I1 minus C1 is positive, then the country has run a current account surplus in the first period. So it's earning interest on lending to the rest of the world, and that could have a positive income effect, which could make you consume more. So that's positive if Q1 minus I1 minus C1 is positive, so you've acquired claims on the rest of the world. Then notice that the coefficient on this is positive. There's a U double prime there that's negative, but the denominator is negative, so there's a positive overall effect. But we're going to assume that the substitution effect always dominates, so an interest rate increase would lower consumption in the first period. Now, okay, points I want to make here. Notice there's kind of a disconnect, if you will, between saving and investment. Oops, I went the wrong way. Our investment doesn't really depend at all on anything that influences that, on our consumption decision. No matter what happens up there with the marginal rate of substitution and the budget constraint, our investment is just determined by that equation on the bottom. So you notice that the utility function doesn't show up there. People's, desire for saving or for consuming today versus tomorrow, none of that affects the investment level. See, that's kind of different from a closed economy. In a closed economy, if people, were big savers, then that would drive down interest rates and that would spur investment, right? And that's how, a macro model would work in a closed economy. Suppose that people say, well, we really care about the future, let's save now. If we save, then there'll be all this saving out there trying to find someone to use it, and that's going to drive down interest rates, and then that will make investment cheaper. But here there's just a complete disconnect between people's desire to save and investment. So that actually led to a whole kind of empirical puzzle that people investigated back in the 1990s. It was called the Feldstein-Horioka puzzle. This is Martin Feldstein, you might have heard of, who was a Harvard economist, and Charles Horioka, who was a Japanese economist. So what they said was, well, really then, investment, if you're looking at an open economy, investment ought to be independent of saving. At least if the economy is too small to affect the world interest rate, investment ought to be independent of saving. But in fact, when they looked at the data, countries that had high saving did have high investment. Okay, it's like a closed economy. We said high saving leads to high investment because it lowers the interest rate. This is saying, well, there doesn't seem to be any connection between saving and investment. And Feldstein-Horioka said, well, that's a puzzle because at least if the countries are small enough they don't affect the world interest rate, there should be no relation between saving and investment. But that actually, that's what they said. And in fact, that was called the Feldstein-Horioka puzzle. But actually, even in the context of our model, we can see kind of what's wrong with Feldstein and Horioka's argument and what the literature subsequently talked about. Because even though you don't see people's utility function in this equation for investment, and so people's preferences for current versus future consumption don't affect the investment level, it's still the case that the variables that affect investment also affect saving. That is, interest rates and productivity affect both investment and saving. So let's actually write down what saving is in this model. Saving would be our income minus our consumption. Income minus consumption. But remember, so this is our first period income. But in this simple example, we set the initial claims equal to 0. So saving would just be Q1 minus C1. So, doing the approximation, ES1 is just DQ1 minus DC1. We solve for DC1 here. So to get the solution for saving, we just have to take DQ1, my laser is running out of battery here. So we just have to take DQ1 minus this solution for DC1, and we get this equation for saving in terms of the exogenous variables. And so, as you would expect, higher first period output raises saving. Higher second period productivity lowers saving. And so why is that? Because if you're going to be richer in the future, then you're going to save less now and you're going to consume more. And if the substitution effect dominates, a higher interest rate would raise saving. So, okay, so we do see that some of the variables that affect the investment affect saving. But actually, this doesn't really resolve the Feldstein-Horioka puzzle because in this model, the ones that affect investment affect saving in the opposite direction. Right? I mean, Feldstein-Horioka's finding was that saving and investment tended to go up together. But remember, you know, an increase in second period productivity raised investment. It's lowering saving. If you have more future income, you save less. But if productivity is higher in the future, you invest more because your investment can earn more income. So that's actually moving the opposite direction. And also the effect of the interest rate gets things moving the opposite direction. So a higher interest rate, assuming the substitution effect dominates, will drive up saving, but it will lower investment. So you know, Feldstein-Horioka's reasoning wasn't really right, that, you know, well, investment is independent of preferences for saving, you know, but, and so, you know, the response is, well, but saving and investment respond to the same variables, but at least in this model, they move things in the opposite direction, so the Feldstein-Horioka puzzle is still there. You know, what the literature then subsequently did was find other models that would imply that those things move together. But we'll come back to that question later in the semester. Okay. Now, what about the current account? Well, now the current account is no longer just saving, but it's saving minus investment. And all we have to do to figure out the effects of these exogenous variables on the current account is to take our solution for saving and subtract off our solution for investment. Okay. So, what are the effects? Well, you know, an increase in current income leads to some more saving. Q1 goes up, there's more saving. It doesn't have any effect on investment, right? Because investment just depends on what's going to happen in period 2. So the only effect of an increase in Q1 on the current account is coming through its effect on saving. We save more. So if current income goes up, we save more. But now what about an increase in productivity next period? Well, you know, that's what we were just talking about. We're saying if productivity goes up next period, we save less today. We say, look, we're going to be rich next period, so we don't have to save as much today. So saving goes down, but then we say, oh, but if productivity is higher, we should invest more because there's going to be a higher return on our investment. The capital is more productive next period. So savings going down and investment is going up, and both of those things make our current account worse. So if you expect future higher productivity, you're going to run a current account deficit. Right. So, you know, one way, I've mentioned this before, but one way to think about, well, why has the U.S. been running current account deficits for an extended time? Well, one possible way to think about it is that we expect high future productivity growth. We, you know, in the U.S. expect high future productivity growth. If we do, then we're not going to save as much because we know our future income is going to be higher, but it also stimulates high levels of investment. So any country that would expect high productivity growth should be saving less and investing more, both of which work to lower the current account. Now, a change in the interest rate, if you're a small country taking the world interest rate as given, has the opposite effect. An increase in the interest rate raises saving, assuming the substitution effect dominates, and lowers investment, and so it raises the current account. Saving goes up and investment goes down. So some people have argued that even from the U.S. perspective, in the long run, the real interest rate depends on what's going on in the rest of the world. All right. So Ben Bernanke, who used to be chairman of the Federal Reserve Board, made this argument that in the long run, the real interest rate is determined by global saving, and when there's a lot of saving in the world, that drives down the world interest rate. So we're just taking R star as exogenous in this model. Now later in the semester, we'll see that if there's more world saving, that'll drive down the interest rate. So that's another possible explanation for the current account deficit. That was Ben Bernanke's explanation, that the world real interest rate is low, and that discourages saving for Americans and encourages investment. And both of those things work to push the current account into deficit. So Bernanke called it the global saving glut. He's saying for some reason, there's a lot of saving in the world economy. A lot of it was coming from China, Japan, Korea, and Germany. That was driving world interest rates down. Americans responded to that by saving less and increasing investment. Okay. All right. Questions about that? All right. So that's our model of reduction. I want to preview what we're going to do in Chapter 5, which is we're going to stick kind of with the model we've been looking at, but add uncertainty. But the preview I want to give you is that I've done this differently than the book. It's actually kind of the same idea as the book. It's the same economic concepts as demonstrated in the book, but I've done it differently. First of all, I mean, if you look at Chapter 5, it says incomplete. They haven't finished writing that chapter. But they only talk about the effect of uncertainty on saving. And they do it all by way of a very simple example. I'm going to do it a little bit more generally. And then I'm also going to talk about the effect of uncertainty on investment. But this is going to take us a while. So really you should be reading not just the book, but you should be reading ahead in my lecture slides and trying to figure it out. Because in this chapter, I'm going to introduce several more mathematical concepts. Again, probably I think this is all going to be reviewed for you, but I'm going to go over it carefully. Now, I promise this is the last math I'm going to add. I mean, after this chapter, there's no new math going to come in. Every bit of math we're going to use all semester will be done with. I mean, we'll keep using math. There's nothing new after this semester, but there's several things that I'm going to talk about in this chapter. One is, expectations, which I know you know about, but I'm talking, we'll review them and talk about people in the model forming expectations as you would with a probability distribution. So when we think about, what's your expectation of Wisconsin's score in the hockey game, we're not just going to say, oh, you expect them to score 1 goal. You're going to, the way we'll model people is you have a probability distribution. You think that there's 20% chance they'll score 0, 60% chance they'll score 1, 20% chance they'll score 2, whatever. So we're going to review expectations. We're going to review variances because those are going to come into play, as you'll see. And we're going to review covariances. All right. So variances And covariance, well, the variance comes into play in thinking about the effect of uncertainty on saving. The covariance is going to come into play in thinking about the effect of uncertainty on investment. So expectation variances and covariances. And then the other thing we're adding in is we're going to do a second order approximation to equations. So instead of this linear approximation we've been doing, we're going to do second order. So it's still a Taylor series approximation, but we're going to add one more term. So all that stuff I review in these notes, and then you'll see it comes in. So how does it come in? Well, we've talked about it. It's a big deal in thinking about the economy today. People talk about it all the time, that uncertainty is influencing the economy. How does it influence it? Well, first of all, it could influence saving. If there's a lot of uncertainty, there could be what we call precautionary saving. Precautionary saving. So if you don't know what the future's like, if you think, maybe you're living in very uncertain times and you don't know whether there's going to be a world war or not, you might want to save additional money as a precaution in case things go really bad. You want to have some extra money on hand. So we're going to talk about precautionary saving and under what conditions individuals engage in precautionary saving. It's surprising to me. I mean, the surprising answer is it does not depend on whether people are risk averse, whether people are afraid of a risky gamble. In our model, we're going to assume everybody is risk averse. Everybody would prefer a sure thing to a risky gamble. But that's not the condition for people to have precautionary saving. Okay, so that's one thing we're going to learn. The other thing we're going to talk about is what's the effect of uncertainty on investment. And there, the answer is going to depend on a covariance. It's going to depend on whether the investment tends to pay off during times when your consumption is low. That would be what you would want. You would want an investment that, other things being equal, an investment that tended to have its best payoffs in times when your consumption otherwise would be low. And then, it has its worst payoffs when you're already consuming a lot anyway. So that would be kind of an ideal investment, is one that says, well, okay, take the average return of this investment is given. What other properties do I want? Well, ideally, I would want this investment to really be paying off when I'm doing badly, when my consumption's low, I've lost my job or something like that. So, and then, it's going to have good payoff, bad payoffs, but those are going to happen when I'm already doing well, so I won't mind the bad payoffs. So so it's going to depend on the covariance of the productivity with your consumption. So we'll see that, and we'll work through all that starting next time. So we're going to go behind the pace that's on the syllabus, because I'm going to take a little bit of time to go through Chapter 5 the way I've written it up. But, really, please read ahead on that. Oh, your homework is back.